if you look at the stare at the data for a second, you will realize that yes, this data is.
So hey friends, welcome back to my channel. And today I thought covering of week 9 and 10. So what I used to do is I make notes while going through the lecture, and in fact I used to make very kind of very deep notes in very depth. That is, I try to write every word that the teacher used to speak in the video, right? So it takes me around like twice the time as that of the length of the video. So, but today I am not going to do that. Today, what I thought is that as I have covered the week 9 lectures already, and so we are going to skim through the video and try to understand what sir is trying to saying and which particular portion we need to focus in order to get a good score in our end term, right? So let's start with the video.
Is linearly separable. Hello everyone, welcome back. So far in this course, we have ways of modeling a binary classification problem. So under super, one is the general examples. Specifically, we looked at the example last time of whereas in think of this as there's a non.
So here sir is describing that we have already covered like the supervision portion to somewhat a good extent, and we have covered in the supervised learning about the binary classification problem, in which we have seen two approaches, right? The generative one and the discriminative one. So in the generative one, there is the idea to model the structure of how the data is being generated, and what discriminates the data from label, say label 0 and label y. That is we are modeling p of x given x and y, right? So from the conditional formula, we know that p of x given y, sorry, p of x and y is same as p of p of uh, yeah. So p of x, p of sorry, we are going to model p of y given x, and which is equals to p of x and y divided by, means there is a division sign, right? Uh, yeah, so the formula is we have to find y, given that the data set, we have to find which label it belongs to. That is, we have to model what is the probability of y given means the feature vector, and its formula from the conditional theory, from the definition of the conditional probability, we know that it is same as having the probability of p of x and y divided by the one in the in we are conditioning with, right? That is divided by p of x. That's p of x, and this could further be written as p of x given y times p of y. So we are dealing with this formula in case of the generative model, while in case of the discriminative approach, we have discussed two algorithms, namely the KNN
The
and
first
the
thing is we are
decision
going to
tree,
look
right?
at
And in these two algorithms, we don't have gone through any modeling story. Like in the naive based approach, we have tried to model that, like there is a say three coins, and we are going to flip that coin, and we are trying to figure out what should be the probability of the coins using the data set. So there is some kind of generative story, but in this case we don't have any such generative story, right? So let's see how the lecture
discriminative
proceeds.
models for classification. So we want to say how does the probability of y equals 1 given x looks like. A feature, now we want to be able to discriminate whether this feature is in class 1 or class 0. So we want to make some assumptions about this discriminating power, right? So what is the functional form of this discriminator? And the simplest assumption that we can make is that it's a linear function. What does that mean? That means the following. So simplest assumption, what is the probability of discriminative models for classification? Where we are trying to understand discriminative model. When you say discriminative model, we want to model p of y given x, right? So we want to say how does the probability of y equals 1 given x looks like, and of course that will determine the probability of y equals 0 given x, which is just 1 minus probability of y equals 1 given x.
So we are now moving from the uh, generative generative approach to the discriminative approach. So actually in the generative approach, we have seen that the decision boundary came for both the case, the linear, the naive bayes and the Gaussian. Both for both of these algorithm, we have seen the decision boundary came up to be a linear one, right? So we have decided if at the end the generative model is going to be a linear decision tree, can we somehow simplify and just do the discriminative analysis? That is like we have to simply model p of y given x. So why we should consider the whole generation of the story? Then we have to track all the parameters, right? So from that paradigm, we are shifting from generative approach to the discriminative approach, and so in the generative approach, there is a problem, like we have to deal with various numbers of probabilities of different parameters. But in the discriminative sense, we don't have to maintain such parameters, right? Like in the KNN neighbors, we have to just figure out how from how many points we are going to ask for their labels. So if there is like five nearest neighbor problem, then we will ask 5 points about their labels, and we will predict the majority one. So there is no kind of probability involved in that case.
So the question we ask is how to model p of y given x, right? So that is you are given a feature. Now we want to be able to discriminate whether this feature is in class 1 or class 0. So we want to make some assumptions about this discriminating power, right? So what is the functional form of this discriminator? And the simplest assumption that we can make is that it's a linear function. What does that mean? That means the following. So simplest assumption, and yes, this is an assumption that we are making on how the data is generated. So this is where we are saying that the probability of y equals 1 given x, right? So this probability can only take two values. It can either be 1 or 0, right? So it's not really a probability. There is a deterministic thing that is happening here, but then trivially we can say that there is a probability of 1 or 0. But when will we say probability of y equals?
So as we are shifting from the generative model to discriminative one, sir is trying to correlate the probability sense, right? There is nothing probability related in this problem as such, but for the sake of kind of a transition, the sir has introduced the probability. So we are going to see in the future there will be no such probability. So we don't have to kind of fear out of the probability here anymore.
1 given x is 1. Well, if w transpose x is greater than or equal to 0, and otherwise, 0 otherwise. Now, remember, let's try to think about what this assumption actually means, right? So, what are we saying? We're saying that the probability that y equals 1 given x is either 1 or 0, which means
Okay, so here in this portion of that is written in the red portion, sir is simply saying that given a data set, either it will belong to the label 1 or 0, right? And there is a kind of absolute certainty that it will either belong to 1 or 0. Nothing, there is uh, we just need to figure out what is this value of x, and we will going to have the dot product. So you know the dot product is between two vectors is given as, so let's suppose there is two vector, right? So suppose there is two vectors, say x and y. So the dot product, that is the x dot y, is written as x transpose y, or we could write we could also write as y transpose x, where x comma y where x comma y have like dimensions, like it is n cross 1 dimension, right? I think you know this fact, and let's move further.
means that let's say somehow somebody gave a feature x. We don't care about how the feature itself was generated because we are only modeling a discriminative model here. So somebody gives us a feature x. Now we have to decide the label y equals 1 or y equals 0, right? So to create, let's say I'm trying to create the training data. Remember, in the generative process of the naive Bayes, we put down the generative story that created the training data. Here also there is a story, but this is a discriminative story in the sense that we don't care about how the x is generated. We only care about how the y is generated given the x, right? So this is the discriminative story. And what is the discriminative story here? Well, if I am going to give you a data set, this is how I would give you a data set. I'll give you some arbitrary x, right? So there is no probabilistic model that is generating x that we are assuming. So I give you an x, but now when I have to decide what is the y corresponding to this x, what I'm going to do is I'm going to toss a coin, and this coin will have either both sides heads or both sides tails, right? So that's what it means to say that the coin has probability 1 or probability 0, right? So when will this coin have both sides heads? Well, when will this coin have probability of choosing 1? Well, when y equals 1, right? So which means that if for the given x, W transpose
So what sir is telling is there we have some kind of not particularly saying that story will be a good idea, but what sir is trying to explain is that there is a story. Let's say there is a story, and we have to figure out um, a, a, a certain variable. Like in this case, we have to figure out what is the value of w. So while trying to predict the level, we kind of have assumed that there is the one. Let's say there is a person x who is generating the data, right? So let's call the person, say maybe I am generating the data, so let's call them Ayush is generating a data. So and you are trying to predict what will be the label given the data set. So what you are going to assume that okay, so Ayush is generating the data, and that data must have a linear sorry a linear a linear structure, right? So we are assuming here,
x is greater than
we are assuming that we are maintaining a linear structure. So you said okay, so I use generating a data such that there is a linear structure maintained, and the linear structure is somehow encoded in this w. So we are going to have the dot product that of the x that is generated and that is giving by Ayush, and what I am going to do is I will try to predict, or try to figure out what is the value of w, such that if the value of this w is going the w transpose x, that is the dot product of this value comes out to be 0, I will go and simply say that okay, the label is 1. Otherwise, I will say it is 0, right? So there is nothing such as hard here, just a simple think that if I will have x, I will simply take the dot product. The dot product turns out to be positive, I will say 1. Otherwise, I will say that okay, it is 0.
or equal to 0, then I would simply say the label is 1. Confuse you. At the end of the day, it is equivalent to saying that simply I'm going to decide the label by checking whether you the data, which means what, right? So this means that what we're essentially assuming about the data is that the data is linearly separable, or this is the linear separability assumption. So let's make that very clear now, right?
So if you recall that in the quiz 2, there is a question on linear separability, right? So we have given 4 data sets and we have to predict like which data set is linearly separable. So the idea of linearly separability is very easy to understand. And let's say uh, yeah, so let's say there is a data set, right? Let's say there is there is some positive things right here, positive data points, and let's say there is some negative data points right there, right? So if there exists any linear separator, right? If there exists any linear separator, uh, wait. If there exists any linear separator, I think you got the point. Yeah, if there exists any linear separator, then we will say that okay, this data set is linearly separable, and this linearly separability means this line is kind of encoded in our variable w.
So what does this mean? This means that let's say I have a data set, I see a data set like this, right? Where green, so where green is red is 0 label, and green has a label as 1, right? So y equals 1. This has y equals 0. Y equals 0. Now, I ask the question, can this data be generated according to the model that I'm assuming? Well, if you look at stare at the data for a second, you'll realize that yes, this data is linearly separable, which means that I see this data. Now, yes, this data could have come from this model that I'm assuming, where there is some unknown w, right? So maybe there should be some w, such that when the
Okay, so I need to discuss a point. So let's say for a linear space, right? In the linear algebra, we have seen that if there is a linear space, let's say this is a plane. Let's say this is a plane. I think yeah. Okay, let's say this is a plane, right? And this plane is represented by a perpendicular vector. So every linear structure is kind of represented by a linear vector. This vector is we call as the normal vector, right? In the vector 3D while studying for the JE or in class 12, we have studied this kind of concept, and even in the linear algebra, that if there is any such linear structure, then we could encode this linear structure using this vector.
when the person who gave me the data labeled the data, the person used some w. I don't know what this w is, but I'm assuming that there is some w. In this case, yes, there is some w, right? So maybe this is the w, which says that everybody on one side of w, the green ones are all on one side of w, the red ones are all on other side of w, right? So for example, then I mean basically this example, we say that this example is allowed under our model. That is, we are putting down this model for the data's label generation process. And well, once you put down the model, then you ask what type of data sets are allowed, right? So this is a data set that is allowed under our model. Now, let us also think about a data set which is not allowed under our model, right? So how would that data set look like? Well, you can again create very simple examples, right? So now here is a data set where you have lots of greens here. Now I ask the question, well, could I have seen this data under the model that I'm assuming? Well, if I have seen this data under the model that I'm assuming, then somebody has given me the labels according to some w. Now, if you look at this example, there is no w such that all the points which have been labeled green are on one side of w and all the points which have been labeled red are on the other side of w, right? So there is no such w. Earlier we said that there is this w, right? So this w, but then this w will not label this point correctly, right? So if the labeler had used this w, then the labeler would have actually labeled this point as green, not as red. But then I'm saying this as red, so this w could not have been the w that the labeler could have used.
Okay, let me clarify one thing. So when we are talking about this linear separator, we will call a data set to be linearly separable if we are able to draw any line, you know, if we are able to draw any line which could separate the data set, then we are going to say that this data set is linearly separable. If we are able to find even a single line, then we are going to say that okay, this data set is linearly separable.
It's not too hard to see that there could be no such W that could have generated this data, which means that we are saying under this situation that this data set is not allowed under our model.
Okay, so in this data set, we could see that this data set is not at all possible to separate it by a line. We need to have two lines in order to separate this data. A line which would go like this, and another line which would go like this. So we need two lines in order to separate the negative points with the positive ones, right? So this data set is not a linearly separable data set.
That is to say that, well, I'm assuming that I will never get such a data set because your model should be able to. I mean, you can only work with data sets which the model can generate. And in this case, we are saying that, well, this data set would not have been generated according to our model, so our model can never explain this data set, right? So now this means that there is no linear separator that separates the greens from the reds in this data set, and so this model is not allowed in our data set. Now one can ask the question, well, this looks like a very simple data set which we should be able to allow in a reasonable model. I agree, right? So any reasonable model should be able to be able to allow the possibility of generating data sets like this where you have these outliers also. Which is a disadvantage of this model, that it only allows linearly separable data sets. But what we're going to do now is, well, we are going to acknowledge that there is this disadvantage at this point, that we are only going to allow linearly separable data sets, and then ask the question, well, if I allow only linearly separable data sets, then how good can I do? Right? So can I develop algorithms which can do the best? If you cannot develop such an algorithm, then even in a simple case, right, so you have made such a strong assumption about the data set, about the model, even under this assumption, if you cannot develop good algorithms, then when these assumptions fail, when you have all these outliers and so on, then it's only going to be hard to develop algorithms, right? So separable data set be able to generate it's the greens from the reds in this data set, and so this model is not allowed in our data set. Now one can ask the question, well, this looks like a very simple data set which we should be able to allow in a reasonable model. I agree, right? So any reasonable model should be able to be able to allow the possibility of.
Okay, so sir is trying to figure out a model which could classify this data, not this data set, but the data set, this one data set, right? So we are having a very restrictive assumption that our data set should be linearly separable, and we are trying to develop a model for the simplest or the most restrictive assumption that we could possibly have on a data set, right? So if we are able to kind of figure out a model for this type of data set, then okay, we may at the later point of stage we may develop an algorithm which could handle this kind of uh, outliers, right? Why I am saying that this is outlier, because all the red points are very far, kind of they are like they have no this point have no relation with this point, so I am telling that this point is an outlier. So we are trying to build a simple model, and if in this assumption if we are not been able to develop a very good model, then maybe we are not be able to classify these points.
Generating data sets like this where you have these outliers also, which is a disadvantage of this model, that it only allows linearly separable data sets. But what we are going to do now is.
So okay, so this data set might look like okay, a reasonable model should figure out that this is a point is outlier, and this that model should divide this data set easily, right? But we are not going to focus on that portion right now. We are just working with this linearly separable data set.
Well, we are going to acknowledge that there is this disadvantage at this point, that we are only going to allow linearly separable data sets, and then ask the question, well, if I allow only linearly separable data sets, then how good can I do? Right? So can I develop algorithms which can do the best? If you cannot develop such an algorithm, then even in a simple case, right, so you have made such a strong assumption about the data set, about the model. Even under this assumption, if you cannot develop good algorithms, then when these assumptions fail, when you have all these outliers and so on, then it's only going to be hard to develop algorithms, right? So we have such algorithms, how you can play around with the algorithm to make it work for this slightly more complicated situations as well, right? So with that understanding, so let's say we make this assumption of linear separability, and now what is our goal, right? So our goal, belonging to some set of classifiers, is this, right? Linear function, even if h is just linear functions, linear hypothesis. right? So which means that if I give you a general data set, which I'm not assuming comes from any model, if I give you a general data set of pairs of x comma y and I ask you to find that line that makes the least number of mistakes, then that's an NP hard problem. Even if you have to just find a line, it's still an NP hard problem. It's a hard problem to solve, right? So what do you mean by a general data set? Well, there is no restriction on how the data set should be, right? So there could be outliers, there could be all sorts of mixing and matching between greens and reds that could happen, right? So in a general sense, if you want to find the best possible line, that's a hard problem. But now
Okay, so mm, maybe I might be wrong in this case of explaining this concept, this thing. But what I have understood from this question is that this is simply the loss, right? Uh, Let me crop this out. Yeah. So this is simply a loss. This is simply a loss for linearly means the classification problem, and this loss is known as 0 1 loss, right? 0 1 loss. This problem is known as 0 1 loss, right? So sir is telling that finding h which could minimize this 0 1 loss is a NP hard problem. Even if we have to just figure out a line, for a line also this problem is an NP hard problem. Now, what is NP hard problem? That is not required in this subject, and frankly speaking, I don't know what uh, means. What I mean to say is frankly hard, but you could think of it like something very hard to compute, or it takes very long time, or very uh, yeah, you can think that an algorithm which takes very long, mm, you say very hard very hard for an algorithm to compute. You are going to say that it's an NP hard problem, and this NP hardness, this is not required at all, right? What you just need to know is that there is this formula is known as a 0 1 loss, and we are trying to figure out a model for the linearly separable assumption. That's all you need from this point, nothing more.
we are saying, well, I'm not going to allow all possible data sets. It's not a general data set that I'm going to deal with. Here's a data set which I'm saying, has a very strong restriction that the data set is linearly separable. That is an assumption that I'm making. But of course, I don't know which is the line that separates the data. I'm just seeing the data. But I know that there is some line that separates the data. Now the question is, under this situation, can I minimize this 0 1 loss? Right. So that's the question that we are going to ask now. How about with x star? What does that mean? That means that
Now from this point of course, we are going to say that we are just going to assume that linearly separability assumption always hold, right? It is going to always hold for our data set until sir is going to say that okay, we are now transitioning to dealing with data set that is non linearly separable. So this linearly separable is kind of pre-assumed, right?
we have a bunch of data points which we know is linearly separable, right? So that
Now the idea is quite simple. We are going to develop an algorithm that could just give me a line. The line could be a good line or a bad line. That is a matter that we will see later on. But this model, the perceptron algorithm, is just going to give you a line. And this perceptron algorithm only works. So there might be a question in quiz like when does a perceptron under which assumption a perceptron algorithm fails or works, right? So you need to say that perceptron as of means as of knowledge till we have till now that this algorithm will work only in case of linearly separable dataset. And at the later point of time, we are going to see that even for a linearly separable dataset, this perceptron algorithm fails. And how we are going to deal with that problem, we are going to see in the next lecture.
that is there is some w such that sign of w transpose x matches the label y. Now under that situation, we know that the labeler is using some w to make these labels. Now for that particular w, what do you think is this value? What is the minimum 0 1 loss? Pause and think about this. I'll tell you the answer now, right? So because the labeler is using a w to think is this value, what is the minimum? Now w transpose x matches the label y. Now under that situation, we know that the labeler is using some w to make these labels. Now for that particular w, what do you think is this value? What is the minimum 0 1 loss? Pause and think about this. I'll tell you the answer now, right? So because the labeler is using a w to label +1 or 0. Now if you had the w access to that w, then you will make 0 errors on the training because that w is what was used to give the labels. If I had access to that w, I'll make 0 training error, right? So the training error can be as small as 0 in this case, right? So you can get a linear hypothesis, which means a line which has 0 training error. Of course, I don't know which line this is, right? So that's hidden from me. The labeler has used some line, but I don't know which line it is. Now the question is it still NP hard to find that?
So again, the same thing, that the whole problem is just to figure out that w, yeah, that linearly separable uh, structure which is separating our data. We just need to figure out that w, nothing more, nothing less. And what sir is claiming, that if we are somehow get uh, get that w, then that w will make 0 loss, because we have getted the perfect w, the ideal w, which is generating the data, and the assumption is that that w will means kind of divide the positive one with the negative one, and if we got that w, then okay, we are simply making 0 losses, right? There is no misclassification, and as a result we are making 0 loss.
Line, or are there algorithms which will help us find this line, right? So now given that we have put such a strong restriction on the data set, now we don't necessarily, we at least hope now that the problem is not too hard matter, right? So it's only that you're given a data set which has some line that separates the one from the zeros. Can you just find this line, right? So can you find a line that does this? It turns out the answer to this problem is yes, we can find such a line, right? So now what we are going to do is we are going to give a classic algorithm which actually tries to find such a line, right? So
Okay, so if you don't able to understand what this is trying to say, what this expression is trying to say is that, so there will be some h, there will be some h. So h is nothing but a function, and the goal of that function is to uh, map this x with some w in order to give a result. Say, let's say y hat, right? So what I mean to say is that h is nothing but it will take value x, and it will give w transpose x, right? And what's the dimension of x right here? The dimension of x is Rn. The dimension of x is Rn, right? And for x and w, the dimension of w is also Rn. Why? Because Rn and Rn transpose Rn transpose means, I think you got the point, right? Like this is my w vector, and this is my x vector, and this is my x vector. The dimension of this w vector needs to be like 1 cross n, not w, it is, this is w transpose, and this one is n cross x, n cross one dimension having, and this is the x vector. Okay, so this is how we are going to dot product. So what this expression is trying to say is that this one you are seeing that here, like something, a symbol like 1. So the goal of means the motive of this one is to just count, just simply count, and it will count that if this one, this condition satisfied. if h of xi, that is w transpose xi, mm, okay, I think here there will be some signum function, right? So what, sorry guys, so means this is first time for me also, right? I have never explained using these videos, and I do, yeah, you could understand how it feels to explain on the way, and I haven't prepared earlier, so I am just like going iterating at this point only. I haven't make a plan like what I am going to say. Maybe that is a good idea. That should what I do, but let's see. Okay, so the goal of this one, yeah, the goal of this one is to simply count, simply count, or you could say that add one whenever this condition holds. Whenever this condition is going to hold, we are just simply going to increase the counter by 1. That's all. What is h of xi? H of xi is nothing but, h of xi is nothing but, it is signum of w transpose xi, signum of w transpose x, right? So signum is simply a step function. How this function is going to look like is that if the x, here we are, here we have x point, if the x is going is negative, like if the x lies in this region, then the answer is simply the -1. Answer is simply -1. Here we could see that there is an open hole, and this point is -1. And for the x which is equals to 0, for the x which is equals to 0, it is going to be 0, and for x which is going to be 1, it is going means for all the positive x we will have a 1, right? And that is what the signum function is doing. So h of x is simply signum of w transpose x1, and we are comparing h of x1 with the actual label. Like for our data set we have xi and the y, and for this portion we are calculating h of xi, and we are just simply taking this and comparing whether it is equal or not. If it is not equal, if it is not equal, then we are going to increment the add increment, and this will have different value for, let's say, for w1. Maybe they, let's say there is, we could, the algorithm could figure out five such linearly separate linear separator, right? Let's say w1 2 3 4 and w5. The goal is to pick which w minimizes this expression, which w minimizes this expression. Let's say if w4 is the variable which minimizes, in fact not, the variable is not a right word, the it is parameter. So w4 is the parameter which minimizes this function. Then we are going to say, okay, w4 should be our parameter. Yeah. So what I mean, I think you got the point, right? Like there is a data set, There is some, here we have positive side, positive thing, and here we have negative things. Maybe say in this region we have negative things, and in this region we have positive things. In this region, uh, okay. So in this region we have positive things, and in this region we have negative things with within this line, right? And there could be multiple such, and there could be multiple such W's, and there could be multiple such W's, and we have to find that W which minimizes the loss, and that W which minimizes. Let's say this is the this is the linearly separator which minimizes the loss. So we have need to figure out this W. That's all this expression is saying. Nothing more.
Let me put down the algorithm, and then we'll talk about more about this algorithm. But before I do the put down the algorithm, let me make this assumption very, very precise, right? So what is the linear separability assumption in more formally stated, so that there is no confusion about what we are talking about. Now we know that the data set satisfies this assumption. Can we find such a W, right? So this is the question that we are asking. Okay, so now let's go ahead and put down the simple algorithm, which is a very classical algorithm. The algorithm that we are going to see is called as the perceptron algorithm, and this was given by somebody called Rosenblatt in the 1950s. So it's called perceptron because Rosenblatt at that point was trying to understand how to recognize objects, right? So the vision problem, a computer vision problem, and he realized that more and more that decision making, the human brain makes decision based on these neurons and synapses and so on. And he got inspired by how a neuron fires, what makes a neuron fire, and he got inspiration from that, and then kind of built this algorithm that we're going to see now, which is called as the perceptron algorithm. So in fact, the history is that Rosenblatt went ahead and built vision can indeed algorithm and a little later. But before that, let's
Okay, so we are going to see the simplest algorithm, that is the perceptron algorithm, and it is developed by Rosenblatt. And sir is discussing some history which is not at all important for the quiz too. So don't I mean waste your energy in the history. Okay, so what is the core thing that we need to figure out from this algorithm? We will going to see.
understand what this algorithm is, right? So what it algorithm, it's easier to compare. So here, the algorithm iteration number.
Okay, so the dataset which we will be provided in the question is nothing new for us. There will be feature vector x. So remember, whenever this, earlier when I am doing this course for the first time, I often get confused, right? Like what is x, what is y, and how it is relating with x and y, everything, and like it kind of confused. This notation kind of confused the new one. But if you try to figure out, like it is very easy. Just you need to see this subject is the most easiest subject. If a student like me are able to score 100, then you could easily score like above 70. There is nothing rocket science going here. You just need to figure out, okay, what's the relation, how the flow is going, what is the core thing, the core concepts, and what is the core formula. That's all what you need to figure out. The core thing means the core concepts and the core formula, nothing more. So the data set is very simple. We have a fixed feature and the label, and this x have the dimension. And in earlier example we have seen that we have the label are like 0 and 1, but in this case sir have taken positive 1 and negative 1. Why we sir used to take this kind of label, we will see.
Number, right? So this is which iteration of the algorithm? This is just a zero vector. So the uh,
Okay, so what this algorithm is like an iterative algorithm, right? So if you try to kind of link the concept with the earlier thing, then you could recall that there is kind of the clustering problem in which we have like the mu1 and then mu2, right? The mean of the centroids. There we have used this kind of notation like this kind of notations of iteration number, and even in the gradient descent problem, like it is discussed in this course, right?
It's a very simple algorithm. Let me put down the algorithm and then we'll talk about properties of this. So the algorithm goes as follows. Until convergence from the data set well, is equal to ii.
Okay. So we have the algorithm now. So this algorithm is one of the easiest algorithm. Okay. So what you need to understand is that, let's discuss this algorithm a bit. Let's discuss this algorithm. Okay. So we could see that first of all we need to initialize initialize our vector, and we are going to initialize this with w0, and w0 will belong to, will have a shape same as that of x, which is in Rd, right? Like this will be a vector of 0 0 0 dot 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 d number of terms, like d number of terms, right? I think you got the point. Now there will be a data set, like let's say this is our data set. Let's say this is our data set. There is like x1 1, mm, wait, there is like x1 1, x1 1, and then we have x1 2, and then x1 3. Let's say that d is equals to 3, and we have y1. So what this first one is, let's say in this example the one is reflecting the instance number, and the later numbers, that is the second dimension, is representing which feature we are talking about, right? And there will be further, like there will be many such instances, like there will be many such instances, and their corresponding y will be there, right? So what we are going to see is that we will pick a point. We will Okay. So what this algorithm is trying to say is that we will pick a point. Then we will calculate this variable, this expression. You recall what this expression is? This is nothing but h of xi, which we have discussed, right? So we will find this, calculate this value, and if this value matches the actual level, if this expression value matches this actual level, then we will just simply do nothing and move to the next data set. Okay, let's say if this point also matches with this y level, we again move forward. Now let's say here the algorithm makes means are not able, this function is not equals to, this function is not equals to yi. Then what we are going to see do is simply update this w, right? And the core thing that you need to learn about in this algorithm is this portion only. This is the, you could say that this is the heart of the algorithm. And whenever, so the idea is very simple. Whenever this expression is not equals to yi, that is our model is making a mistake, we will update the parameter w. How we are going to update this parameter is, we are going to take the xi and we are going to multiply with this yi. So let's say okay, so in the next lecture we are going to see how this we are going to elaborate this uh, updating step, right? So the idea is very simple. Just update when the model is making mistake. Update when the model is making mistake. And you must note a point that is very crucial. Let's say here you make a mistake, then you update the parameter, and further you move on, and there is no such mistake. Let's let's say there is no such mistake. Then after updating this parameter, after updating this parameter, it might happen that for the earlier assumption, means the earlier, that is wt is making correct predictions with respect to this samples, right, these two samples. But wt plus 1 may go wrong. When we have updated from wt to wt plus 1, then wt plus 1 may predict wrong for these two samples. So we have to again check for these two sample as well, right? So let me repeat once again. So we got w. Let's say we are in at some iteration wt, and we have some points as well. Let's say w1, w2, and w3. Why 3? Because we have three features, right? And in general, these three could be d. That's all. So this wt is making correct prediction for this and for the second level, but it turns out that it makes a wrong prediction in this case. Then what we will do is, we will use this formula and update this wt to wt plus 1, right? So what I am trying to say is that after you figure out that okay, we got a new wt plus 1 here, and we will further move on, and the wt plus 1 makes no mistake in this portion too. But this portion may be wrongly classified by this wt plus 1 parameter. Make this thing very clear in your mind, that wt plus 1 could made mistake in this region, right? So as a result of which, you have to again check for the whole data set. You have to again check for the whole data set whether it is making correct prediction or not. If we are able to get a wt plus 1 which classify all the points correctly, then we will say that the algorithm has converged. I am repeating, if we are able to find any w, if we are able to find any w which classify all the points correctly, that is there, this expression value is same as that of w y1, then we will say that okay, the algorithm has converged. Otherwise, this algorithm will never converge, right? So let's say wt, you got wt plus 1, then some other point is making mistake, and you go through the whole the data set, and you find that okay, this instance is making mistake. You update this wt plus 1 to wt plus 2, again some points is making mistake. So it might happen that this algorithm may never converge. It might happen, right? But in future we are going to see that this algorithm will indeed converge, provided the dataset is linearly separable with some gamma margin. That concept will be introduced in the next lecture. Okay, so this is the overall algorithm. I think you got the point, and we will dissect this expression earlier. Means in the future, we will dissect this algorithm as well. Uh,
One problem, initialization that classifies all points in your data set point, then you update your W based on that point, right? W update rule, which is WT plus 1 is WT plus XI YI. Now remember, XI is
okay, just for a quick introduction, like WT is the in previous means the W in the previous iteration, that Tth iteration, and Xi is the data point, right? So Xi will
in
be
RD.
like okay, there some of you could make mistake here also. So you could think that okay, we are doing a dot product, right? You might think that we are doing a dot product here also. So you may say that okay, it will give a this whole thing x I and yi will give a scalar, but that's not the case. So you recall you w I have said that okay, y sir is taking wi belongs to -1 and +1. This is the reason, because let's say if we take 0 and 1, then we aren't able to we aren't able to update this parameter in case of the incorrect classification, in case of when the this expression is predicting wrongly for 0, right? Like actually it is 0, but it is this expression is predicting 1. In that case, we will we wasn't able to update this wt plus 1. That's why we end up making this data set like this, means encoding the y as -1 and +1.
Yi is plus or minus 1, depending on whether the point was labeled plus 1 or -1 in your data set. So all you're doing is, you are maintaining a current W. You are looking at all the points in your data set. If you can find a point where the current W is going wrong, then you make an update to the current W based on the point where you made a mistake. That is, you take the point xi yi where the current WT makes a mistake, and then just add xi into yi to your WT to get your new W. And now for this new W, you go through all the data points, see if it matches, if it predicts correctly all data points. If it does, then you're done. You found a W that works, that has zero error. Otherwise, you would have found a point where this W makes a mistake, and you will add that point in multiplied by its label to the current point, and you keep doing this. Now, what I'm saying is that if you keep doing this, then I'm claiming that this you do this until convergence, right? So that's a statement that needs some clarification, right? So what do I mean by convergence here? Well, we'll say that the algorithm has converged if just end the algorithm. Um, Now the update rule is the only thing that is non-trivial happening here, right? So the only non-trivial step which is happening, which is a very simple step in this algorithm, is the update rule. It says that if you make a mistake, then add that point times its label. What is the guarantee that this algorithm is going to converge? Right? So because I'm kind of adding a lot of things to my W, I'm keeping on updating my W. What is the guarantee that I will actually find a W that
Okay, so in so sir is saying that okay, we have this beautiful algorithm, but the problem is that we will able to find W only when this algorithm converges, right? So we are going to see a mathematical proof, like whether this algorithm will actually converge or not. So in the later point of time, we will see that algorithm, and I will discuss there also that what things you need to pick up from this overall derivation, right?
eventually correctly classifies all the data points. Not clear at all at this point. So the moment I say until convergence, that needs to be backed up with an argument. So what we are going to do is we are going to understand whether this algorithm will actually converge or not. And to understand that, we first need to look closely into this update rule, right? So because that's the only non-trivial thing happening in this algorithm. So we want to understand if the update rule is doing the most reasonable thing that we want it to do, right? So that's the first thing that we are going to think about. So let's start understanding the update rule of the perceptron algorithm to see what it is trying to do.
Okay, so we have successfully completed this lecture. So what I thought is that to continue all the to cover all the lectures of week 9, but when I started recording, like it is kind of a bit paining for me in my, like I am talking, it's kind of like 1000 for, I mean one, not 1000, 1 hour straight, so it is kind of paining for me, right? So let me have a break now. So I will kind of post this video in the WhatsApp group if I got a decent amount of, like, if 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 I am going to have a decent amount of feedback from your side, like I am actually liking the way you are explaining things, then we will continue further, right? And I will really appreciate your feedback, like where I could improve myself. Okay, so let's hope for the best. Thank you.